Evening. Today we'll be focusing on exercise 2.1, single phase transformers. These are 7 questions that I will answer on this video. Okay, so if we look at question number 1, question number one tells us that the magnetic core of a transformer is found to carry a flux of 0.075 sine 314 T Weber. Determine the RMS value of the induced voltage in a 110 coil wound around the core. Firstly, 1.1, do this using Faraday's law. 1.2, use the transformer equation. 1.3, if the cross-sectional area of the core is 25 cm squared, determine the flux density in the core. Assume a uniform flux distribution. Okay, so what I did, I wrote down values that are given in this question. So here I wrote flux T is equals to 0.075 sine 314 T Weber. So it was given to us in this form. This is the form in which we were given the flux. This is per Weber. Okay, so we know this part, which is 0.075, is our maximum flux. Okay, it's our maximum flux. And we know that 314 is our rotational speed. Okay, it's our rotational speed. So what we're gonna do, and then our n is equals to 100. So what we're gonna do, we know that every time we do calculations, we have to use RMS values. So first of all, we will have to convert the maximum flux to RMS. Okay, so to convert to RMS, we're gonna say flux maximum divided by root 2. Okay, so 0.075 divided by root 2. This gives us 0.053 Weber. Okay, so we can write it in this form. We can say this is 53. 1, 2, 3. This is 53 milliweber. So this is the RMS flux. Okay, so 1.1, let's say use Faraday's law. First of all, we know that the Faraday's law, what it means that the law states that whenever you have a change in magnetic field, that change in magnetic field, if it cuts a conductor at right angles, or the opposite happens, an induced EMF will be present inside the conductor, which is equal in magnitude but opposite in direction to the supply voltage. So we see this by the equation, that is E, which is the E represents the induced EMF. It represents the induced EMF. So we have E is equals to negative number of turns, change of flux with respect to time. Okay, that's why it's negative, because it's opposite. This is what they mean by we must calculate the induced voltage using Faraday's law. Okay, so right now what we're gonna do next is that we're gonna take the rotational frequency, the rotational speed from the flux that were given. Okay, it's 314. Okay, this is 314. This is the rotational speed. Okay, so we know that rotational speed is equals to 2 pi f. Okay, this is the equation for the rotational speed. So in this equation we're not told anything about the frequency, so that's what we use this equation to get the frequency. So 314 divided by 2 pi, which is equals to 60 hertz, is equals to 60 hertz. Okay, so we know that in this equation what we have, we're gonna need a changing flux in the equation of the induced EMF. We're gonna need a changing flux. Okay, a flux that changes from between maximum and minimum. It goes to maximum, it changes back to minimum. Okay, so we're gonna need the flux to change. Okay, so we already have the flux, so we know that when the flux is at the maximum, it is above the positive axis, and then the moment the flux changes and then it goes opposite, it goes below to the minimum, which is at the negative axis. So you're gonna have the final of the flux, which is 53 positive, subtract the negative, which is the minimum, which is the flux when it is reversing in the opposite direction. Okay, so we're gonna deal with that. Okay, so right now we just have to make sure that everything that we need in this equation, we have it for us to start calculating. Okay, so far we have the changing flux, we have the number of turns. Okay, what we need is the time. So we need to know if this flux reaches its maximum of 53 milliwebers and then it reverses to the negative side. Okay, how much within how much time does it do that? Okay, within how much time? We need the time. Okay, the time period. So what we're gonna do, we know that we have the frequency now. Okay, and then we know that frequency is equals to 1 over t, which is the period, which is the time. So t is equals to 1 over f, which is equals to 1 over 60, which is equals to 0.02, 0.02 seconds, which we can write as 20 milliseconds. Okay, 20 milliseconds. So what does this mean? This is the period. Okay, this is the period of the signal of the flux when it is alternating, when it is changing, I can say, from between maximum and minimum. Okay, this is the time that it will take. So I'm gonna leave you to copy what I wrote on the screen. So I did copy everything that you see on the screen before I erase everything. Okay, because I'm gonna erase to create space. So I need you to do that for me. Copy on the screen. Okay, copy on the screen. Okay, copy on the screen. Copy on the screen. So I suppose you copied. Okay, so let me erase, because we have the information now. So now let's calculate the induced EMF. Okay, let's calculate the induced EMF. You know, I'm gonna be doing this erasing thing in every question that we do, because I'm running out of space. Okay, so we know T is equals to 20 milliseconds. Flux RMS is equals to 53 milliweber. E is equals to negative n, change of flux over change of time. So this is equals to minus into 100 into 53, subtract final minus minimum. Minimum is negative because it's the negative axis of the signal. Okay, times 10 minus 3 divided by 20 times 10 minus 3. Okay, so we get the induced EMF, which is negative, to indicate that it is positive. It has to be negative. Okay, it has to be negative. This is 530 volts. So this is our induced EMF if we use Faraday's law. Okay, so one thing I can say after solving this question, I hope it was straightforward. What I can say is that in question 1.2, they're telling you to calculate the induced EMF using the transformer equation, but you need to understand that this is the transformer equation that we're going to use in the next question. It's like this. Okay, so these two equations are not the same. Okay, they are not the same because the first equation respects time. Okay, it's like it's more like I can say an instantaneous, instant, meaning with time. It goes with time. It cuts the changes of the flux with time. Okay, so the next equation has no time, does not respect time. So I don't think using the two equations you can get the same answer. Okay, so we don't have to be confused if we calculate 1.2 and we get a different value. Okay, so I hope that makes sense. So let's answer question 1.2. Okay, let's answer question 1.2. Question 1.2. 1.2. Okay. 1.2. 1.2. Calculate the induced EMF using the transformer equation. Like I said, this is the equation. Flux max, frequency, number of turns. Okay. Frequency, number of turns. Frequency, number of turns. Alright. So the difference in this equation is that on the flux we're gonna substitute the flux as a maximum. So we're not gonna use it as an RMS. Okay. We're not gonna use it as an RMS. We're gonna use it as it is because it's maximum. And then this is the frequency, and then this is the number of turns. So the induced EMF is equals to 4.44, flux 0.075, frequency 60, number of turns 100. Okay, number of turns is 100. So calculating the induced EMF gives 1,998 volts. This is the induced EMF using the transformer equation. Okay, so I hope that was a straightforward alternative to the answer. Okay, so 1.3, it says if the cross-sectional area of the core is 25 centimeters squared, determine the flux density in the core, assuming the uniform flux distribution. Okay, so in this case they're saying if you are given area as 25 centimeters squared, okay, if you're given the flux as 25 centimeters squared, determine the flux density in the core Okay, so we're simply gonna substitute everything that we have so far. Okay, everything we have so far. All right. So what we're gonna do, we're gonna make, you know that flux max is equals to B max times area. Okay, this is the equation. So we're gonna break the equation into 4.44, and then the flux part we break it into B max times area, and then you have the frequency and then the number of turns. So for B max, as a subject of the formula, we will have 4.44 area, frequency, number of turns, and then at the top we'll have E. Okay, so what we're gonna do, we're gonna substitute everything that we have. Okay, we're gonna substitute everything that we have. Okay, I wanna see something. Okay. Okay, so we're gonna substitute everything. Okay, so we have B max is equals to B max is equals to 1990. Oh, sorry. 1998 divided by 4.44 into 25 brackets 60 times 100. So this gives 3 milliweber. 3 milliweber. Okay. 3 milliweber. That is our flux. Okay. So let me just double check on that one. If I didn't make a mistake, let me calculate again so that I see if I did not make a mistake. Okay. If I didn't make a mistake. Alright. Yeah. Everything looks fine. Okay. So that is our flux density. Okay. That is our flux density for 1.3. Okay. So let's move on to question number 2. Okay. Let's move on to question number 2. So likewise, I'm erasing everything, guys. I really need space, and I need to get to question 7. Okay, so I need to make sure that everything that I write on the screen is clear and understandable. Okay, for you guys who will be watching. Okay, that's what I need. That's really what I need. Okay. So question 2. Question 2. What does it say? A coil wound around a magnetic core sets up a flux of 0.001 Weber, which is RMS. When 230 volts 60 Hz supply is applied to the coil, determine the number of turns on the coil. Okay, so we have that question. Okay, we have the question. So they're looking for the number of turns on the coil. So like I said, always write down what you're given. So we're given flux RMS is equals to 0.001 Weber. We're given E. Okay, we're given E is equals to 230 volts. Given frequency is 60 Hz. So we're looking for the number of turns. Okay, so this looks easy to answer with the transformer equation. Okay, I like this equation because it's straightforward. So we don't have the number of turns, we have the frequency. We can convert the RMS flux to maximum, so we'll have it, and then we also have the induced EMF, the voltage that is applied. So what we do, we want to say flux RMS equals to flux max over root 2. So flux max is equals to root 2 times 0.001, which is how much? I'm calculating. Is 1.414 milliweber. Okay, so that is the maximum flux to put inside the equation. So now that we have everything that we need, let's make number of turns the subject of the formula. So we're gonna have let me write it properly. We're gonna have 4.44 flux max times frequency. This is E over everything. Okay, so we have 230 over 4.44, okay, into 1,414 times 10 power negative 3 into 60. Therefore, the number of turns is equals to 6. Wait, I'm seeing something. Okay, yeah, I got 610.58. So I'm gonna round it off, okay, and it becomes 611. So that's the number of turns that I needed. So we solved question number 2. Okay, and as you can see on the right hand side for number 2, yeah, there it is 611. Okay, so those are the number of turns. All right, so now I hope it was straightforward to answer. I hope it's understandable. So we're gonna move on to question number 3. Okay, moving on to question number 3. Question number 3. Question number 3 says a transformer has 100 turns on the primary and 25 turns on the secondary. The secondary voltage is 115 volts. Determine the primary voltage. Okay, so one thing I can teach and I can say is that in such a question whereby you're only told about turns and voltage, okay, they never told you anything about resistance. So I usually like to assume that V1 is equals to E1 and E2 is equals to V2 in such questions. Okay, I assume the conditions for an ideal transformer. That's what I assume, because nothing was mentioned about the impedance, nothing was mentioned about the resistance. In the question, there's no way whereby they tell me to calculate the resistance. So I know that if there's no impedance or there's no resistance or it is negligible, I know that V1 is equals to E1 and E2 is equals to V2. That's what I know. Okay, so in other words, what I'm saying that the secondary voltage in this case, let's call it E2, induced EMF 2, okay, which is 115 volts. So the number of turns N1 is equals to 100, and then N2 is equals to 25. Okay, so the transformation ratio is known as E1 over E2 is equals to V1 over V2 is equals to N1 over N2, okay, which is also equals to I2 over I1. So for us, we're going to equate this thing to E1 over E2 is equals to N1 over N2. We can take this and consider it as an equation that is useful in such questions. So always remember this formula. It's very much important. Okay, so we know that we have N1, we have N2, we have E2, so they need E1. Okay, that's what they're asking us to calculate, is the primary voltage. Okay, so we're gonna make E1 subject of the formula. Okay, N2 N1 times E2. So now we substitute everything. Okay, so N1 it's 100, N2 is 25, and then E2 is 115. Okay, therefore E1 is equals to 460 volts. So this is what they're looking for. Okay, this is what they're looking for. So I hope it was not a challenging question. Okay, I hope it was straightforward. So I would like us to move on to question 4. I hope I'm not that fast. Okay, I hope I'm not that fast. So I hope whoever's watching is copying everything and writing it down, noting it. So if I'm fast enough, I'm thankful. So please, if maybe I'm fast enough, pause the video and copy whatever that you see on the screen. Alright, moving on to question 4. Alright, question 4. A 100 kVA 4000 200 single phase ideal transformer is delivering rated load at unity power factor. The induced EMF per turn is 2 volts. Okay, determine 4.1 the secondary current, determine the primary current. 4.2 4.3 determine the number of secondary turns. 4.4 determine the number of primary turns. Okay, alright, I always say, always write down what you are given. Okay, so in this case we are given the apparent power, which is 10 kVA, and then you have 4000, and then you have 200. So this is, we are told that it's one single phase. Okay, and then we are given the induced EMF per turn of 2 volts. Okay, so okay, before going to the question, what is the induced EMF per turn? What does it mean? What does it mean? Okay, the induced EMF per turn simply means that this is the voltage that becomes induced inside 110 is the voltage across 110. This is the induced EMF. So inside 110, between here and here, inside the 110 is the induced EMF. Meaning if I add another 10, like this, my induced EMF is still 2 volts. But now I'm gonna add them, meaning I'm gonna have 4 volts. Okay. But inside 110. That's why we were saying induced EMF per 10. The induced EMF is the voltage that becomes induced inside 110. Okay. I hope someone understands that. Okay. So we can solve 4.1. Determine the secondary current. Determine the secondary current. Okay. Alright. So I like another equation, which is I times E. Okay. S is equals to I times E. Okay, I times E. So this is full load 2. This is E2. Okay. So the current depends on what we are dealing with. If we are dealing with full load current, I will write I full load. If maybe I'm in another kind of question whereby I'm dealing with fault currents, and I can use the same equation and put fault current I fault. So yeah, in this case it's secondary current. Okay, secondary current, full load. Okay, so yeah, I'm saying full load because in question number 4 we're told that a single phase ideal transformer is delivering rated load. Rated means full load. Okay, so it's the same thing. Rated means full load, meaning they're saying that a ideal transformer is delivering full load at unity power factor. Rated, full load is the same thing. Okay, so right now I'm gonna make I full load the subject of the formula. Okay, so S is equals to 10 times 10 to the exponent of 3 to the power of 3, I mean. Okay, and then this is what is 200. Okay, so that gives us 50 amperes. Okay, it gives us 50 amperes. All right, and then 4.2 gives us we're gonna use E1. We're gonna use E1. Okay, we're gonna use E1. So we're gonna write the same equation, and then we're gonna make I full load 1 subject to the formula. S is equals to E1. This is equals to 10 times 10 power 3 divided by 4000. This gives us 2.5 amps. Okay, this is the current for I full load 2. This is 4.2. Okay, this is 4.2. So as we move forward to 4.3, I hope I haven't lost anybody. Okay, determine the number of secondary turns. Determine the number of secondary turns. The number of secondary turns. Okay, so like I said, one thing that you should know is that the EMF per turn is the same for both sides of the transformer. High voltage and low voltage induced EMF per turn is the same. Okay, so in this case, for the number of induced EMF per turn, like it says EMF per turn, so meaning E10, because it's EMF per turn, so I'm looking for secondaries E2 over N2. This is the equation for induced EMF per turn. Okay, it's E over N, induced EMF per turn. Okay, so this is E2. I have 200. Number of turns for the secondary side. Am I given? No, I'm not given. Oh, it's what I'm looking for. If I'm confused, sorry. Oh, I'm confused. I made a mistake. We're looking for the number of secondary turns. Yeah. So it's E2. I make it some sort of substitute formula over T. So this is E is 200 over 2, which gives us 100. The number of turns is 100. Okay, for the secondary number of turns. Okay, so for number 4.4, we're gonna take the same formula and then we make N1 is equals to E1 over induced EMF per turn. Okay, so this is E1 is what is 4,000 divided by 2, which gives us 2,000. This is the number of turns on the primary side. Okay, it's the number of turns on the primary side, 2,000. All right. So we answered question 4. Okay, I hope everyone understands how I'm solving the questions. Okay, I'm trying to be as slow as I can. Okay, I hope I'm not confusing anybody. Okay, so we can move to question 5. Okay, so let's move to question 5. I will cancel everything, but please copy, huh? Please copy. Okay, I'm giving you time to copy. Just a bit of time for you to copy. So I hope you're done copying. So because I'm gonna erase everything. All right, so let me erase everything. Okay, everything. So now we are moving to question 5. We are moving to question 5. Where's my pen? All right, question 5. A 25 kVA transformer has 500 turns on the primary and 50 turns on the secondary winding. The primary is connected to a 3000 volts 50 Hz supply. Determine the primary and secondary currents on full load. That is question 5.1. 5.1. Okay. All right. So always write everything that you are given. S is equals to 25 kVA. Okay, N1 is equals to 500. N2 is equals to 50. So we have 3,000. No? We have 3,000. So we have E1 is equals to 3,000 volts. Okay, so frequency is 50 Hz. Okay, this is the primary and secondary currents on full load. All right. Okay, Like I said, S is equals to I times E full load. The one word primary, secondary. Or let's start with primary. I full load 1 and E1. Okay, so I full load 1, it's equals to S over E1, which is equals to 25 times 10 power 3 divided by 3000. So the answer gives us 8.333 amperes. That is the answer for the primary current on full load. Okay, primary current on full load. So like I said, one thing that we have to know, now we have to calculate the secondary. I full load 2. Okay, so we know that N1 over N2 is equals to E1 over E2, which is also equals to I2 over I1. So in this kind of question, what we can do is that we can equate the equation for it to be N1 over N2 is equals to I2 over I1. So we can find I1 using this equation because we have the number of turns. We have the number of turns and then we have I1. Okay, so we can use that equation. Straightforward. It's just once you need to focus. So the equation that we are using is N1 over N2 is equals to I2 full load 2 over I full load 1. So we have I full load 1, so we can make I2 full load subject to the formula times I full load 1. So we have 500 over 50, okay, times 8.333. Therefore I full load 2 it's equals to I'm calculating, this is equals to 83.333 amperes. Okay. I hope we're still together. Okay, I hope you're still together. So this is an interesting thing when you play with the equations. Okay, it's important to know equations because one thing that makes machines difficult is that in machines 2 and 3 they don't give you formula sheets, so you have to make your own formula sheets and understand what's going on. Okay, you should always put things in mind to remember. That's what makes machines to seem difficult, but machines is not that difficult. Okay, it's not that difficult. So yeah, this is how we get to the answer, because no matter what you do in the calculations, do not forget that you'll always have KT, the turns ratio. So remember N1 over N2, E1 over E2, I2 over I1. Those things are very much important. You should always keep them in mind. You must never forget them. They're very much important. Okay, so I hope answering this question was clear. Okay, so let me create space for question 5.2. Okay, question 5.2. Okay, Alright, question 5.2. 5.2. High full load 1 is equals to 8.33 3 amperes. High full load 2 is equals to 83.333 amperes. 5.2. Determine the induced EMF of the secondary. Okay, remember the equation that we used. Okay, E1 over E2. We use the same equation. Simple and straightforward. Okay, induced EMF 2 is equals to N1 over N2. I know I'm not doing it right. Not doing it right. I'm not doing it right. Alright, it has to be E1 times N2 over N1, which is equals to 3000 into 50 over 500. So E2 is equals to 3000 this is 300. It's 300 volts. This is E2. Okay, this is E2. Alright, this is E2. So understanding how I answered the question, so we are done with question 5.2. Okay, so we can move to 5.3. Okay, 5.3 says determine the flux in the core. Alright, determine the flux in the core. So it's up to you. It's up to you whether you determine the flux in the core using E1 or you're gonna determine the flux in the core using E2. Either way, it's gonna give you the same answer. So we can prove that. Okay. Remember, the EMF equation is always in handy. Okay, it's always in handy. Always in handy. So frequency, number of turns. So let's use E1. Okay. So the flux will be equals to everything 4.44 and then frequency, number of turns, E1, number of turns, because this is E1 must be also number of turns 1, number of turns 1. So this is 3000 divided by 4.44. Frequency is 50 Hz, 50. The number of turns N1 is 500. Therefore, the flux max is equals to, let me calculate. Okay, 3000 divided by 4.44, 50 into 500. Okay, this gives us 0.027, which becomes 27.027 milliweber. This is the flux. Okay, this is the flux inside the core. So you can use E1. Okay, here in this case we used E1. So I'd like to show you if maybe you decide to use E2. It's also possible, you'll get the same answer. So we can do that. Flux max, if you chose E2 4.44, frequency and 2, number of turns, equals to 300, 4.44, 50, 50. Okay, gives you how much? Gives you the same thing. Okay, let me calculate. 4.44, 50, 50. You see? Exactly the same answer. They're getting exactly the same answer. 27,027 milliwebers. So it doesn't matter whether you use E1 or use E2, you'll get the same answer. So it's up to you. Okay. Alright. So we answered question 5.3. So now we can move to question 5.4. Okay. We can move to question 5.4. 5.4. 5.4. Okay. Okay. If the load power factor on full load is 0,8 lagging, determine the output power and draw a phasor diagram for this question. Okay. Okay. Alright. 5.4. One thing about a transformer that you should know is that output power of a transformer is equals to N S cos phi 2, which is the angle of the impedance, and then the N is equals to I short circuit over I full load. This is the N. So this N, I like to call it percentage of full load. Okay, because this N tells us how much is the load current flowing inside a loop of a coil. For example, if the transformer, the current that's flowing the transformer, is the total current or of the rated of the windings, meaning it's full load. If it's full load, then N is equals to 1 per unit, which is 100%. So we are saying the current that is flowing inside the transformer is flowing totally. The total current is flowing. But what happens if we are inside the windings of the transformer, half of full load is flowing? What happens if only half of that amount of current is flowing? What happens if 100% is not flowing? What if 50% of the current is flowing? So N will be equals to 50%. In that case, N will be equals to 0,5 per unit. So that's why I call it the percentage of full load, because it tells you, you know whether your transformer is operating under total capacity, or under half capacity, or under quarter capacity. Okay, so it's the percentage of full load. This is the N that I'm talking about. All right, so one must always keep that in mind. Don't be confused. Okay, so based in 5.1. Okay, based in 5.1. So how much will be our N? Okay, in this question our N will be 1. Why am I saying this? I'm saying this because in question 1 we're told that determine the primary and secondary currents on full load. So we know that the conditions are under full load. Full load means rated. Rated means N is equals to 1. So we know that N is equals to 1 already. Okay, so already we know that N is equals to 1. Okay, so what are we gonna do? We're gonna check. Okay, we already know S also. How much is S? We know S. S is 25 kVA. Okay, S is equals to 25 kVA. N is equals to 1. Our power factor, we're told that is 0.8 lagging. So we have everything to calculate the output power. We have everything to calculate the output power. Okay, so we're gonna need the angle. We might need the angle. Okay, so 0.8, the angle will be 36.87 degrees. Okay, so we simply take the power factor, the N, and the S. We substitute inside this equation. So P out is equals to 1, 25, 0,8, which therefore is equals to 20 kilowatts. That's our output power. Okay, that's our output power. Question 6. Question 6. Question 6. Okay. Question 6. What does question 6 say? Question 6 says that a 300 kVA 460 115 V 50 Hz single phase transformer supplies a load impedance of 30 plus J40. Question 6.1. Determine the primary current. Okay. Determine the primary current. Okay. So we are given the load, the value of the load. Okay. We are given the value of the load. The value of the load. Alright. First of all, write everything that we are given. Okay. We are given S is equals to 300 kVA. And then we're given 460 is 115 volts, frequency 60, no, it's 50 Hz, frequency is 50 Hz, 50 Hz. Okay, this is single phase, ZL load 30 plus J40, this is ohm. Okay, 6.1. Determine the primary current. Okay. First of all, don't forget to always put your KT ratio in line, because it might help you. Okay, it might help you. It might help you. Okay, V1 over V2, phase 460 over 115, 4. Okay, so we know the values of our KT. KT is 4. So now we can calculate. We need primary current. Primary current is I1. Okay, primary current is I1. So maybe you might be confused. Why am I using V1 in this case? Why am I not using E? Okay, if you check, we're given the Z load. So we're given the Z load. You know that a transformer looks like this. Simple way to represent it. Okay, looks like this. So this is Z2, this is Z1, this is the supply, it's V1, current flows, and then there's a volt drop, and then across this you have E1, you have E2, here's volt drop, Z2, V2, and then at the terminals, where there's the load, at the terminals, Z load, the voltage across Z load is V2. Okay, it's V2. So if right now I have Z load, I will have to say, okay, the current that is flowing here it's I2. So if the current flowing here through this loop, it's I2, meaning I can say V2 is equals to I2 Z log. This can be my equation. Okay, so right now if I put E2, it's gonna be a problem because I'll have to use the transformation ratio to convert to the other side. So it's easy for me to say V2 because from the load side I'm solving using V2. So for me to transform the V2 to the other side, it has to be in line with V1. KT is equals to V1 over V2. Okay, because V2 will be here. I cannot say E1, E2. This is V2 in this case. So machines depends on how in every question you are asked. Okay, how in every question you are asked. So the way we are asked in this question, it's right for us to represent the equation as V1 over V2. Okay, but in the other questions, it was also right for us to represent the question using E1 over E2. So it depends on how the question is asked. Okay, always remember that. That's machines for you. Okay, so I hope I'm making sense. All right, so now we can solve for I2 because this is V2 is equals to I2 Z log. So I2 is equals to V2 over Z log, which is 115 at an angle of 0 degrees over 30 plus J40. Okay. All right. I'm still calculating. Gosh, it's taking long. 30 plus. Okay, I'm getting how much is this? Yeah, 2.3 angle minus 53.13 amperes. This is what I'm getting. Okay, for I2. So now that I have I2, I can come and say I can come and say I KT. Okay, KT is equals to I2 over I1, and then I make I1 subject of the formula. So I get 2,3 angle minus 53.13 over 4. Therefore, I1 is equals to this is 0.575 angle minus 53.13 degrees amperes. So this is the current of I1. This is 6.1, so we answered 6.1. This is the current for I1. okay, is the current, it's the primary current. Okay, I hope it was not that difficult. Okay, I'm glad because we're almost done. We're almost done. Okay, and I always say to people that, you know what, direction is better than speed. Okay, I know maybe I'm a bit slow. It's a good thing that I'm slow. I'm not fast. It's a good thing that I'm slow because I want people to understand. Okay, so it doesn't matter how long the video takes, as long as someone understands. That's what matters the most. Okay, so we can answer the second question. Okay, the second question. 6.2. Okay, determine the load impedance referred to the primary. Okay, determine the load impedance referred to the primary. Okay, this is straightforward. Okay, the rule says that if you are transferring impedance from secondary to primary, you're gonna multiply. Okay, you're gonna multiply by kt squared. Okay, so in this case, because we're gonna transfer the load, so we're gonna have z prime 2, meaning is the one that will be on the primary side after it is transferred. So z load is the one that is still in the secondary before being transformed, times kt squared. Referring secondary to primary. Okay, if this is your impedance, it doesn't matter whether it's impedance or resistance or reactance, whatever it is on the secondary, you take whatever that is on the secondary, you multiply it by kt squared, and then it's going to give you the value of how it is on the other side. Okay, so if my z load of the secondary, I multiply it by kt squared. Okay, and then it gives me z prime 2 on the other side. Okay, that's how we do it. That's how we do it. So for this one, okay, if referring to sorry, referring primary to secondary, z prime 1 is equals to z load divided by kt squared. So here you divide kt squared, here you multiply. Sorry. So the difference between these two is that when you're taking whether resistance or impedance or reactance from primary side to secondary side, you're going to divide it by kt squared, the transformation ratio squared. Okay, so your new value on the secondary side will be called z prime 1 or r prime 1 or x prime 1. Okay, so on the other side, referring secondary to primary, what is resistance or reactance or impedance on the primary side is going to be called z prime 2. That's the new value. But what do you do is that whatever value that it is on the secondary side, you take it and then you multiply it by the transformation ratio squared. You multiply here, you multiply here, you divide by kt squared. That's how you refer. Okay, so information on how we arrived to this, how we derived it, I'm gonna make it on another video. Okay, not here, because here I need to close soon. Okay, soon I need to close. Okay, so we can answer the question because I explained 6.2. So our Z load prime, okay, Z load prime is equals to 30 plus J40 plus 4 squared. Therefore, ZL prime is equals to 480 plus J 640. Okay, plus J 640. This is ohm. So that's our referred load impedance. Okay. So that's our referred load impedance. Okay, it is referred. So that's 6.3. Okay, so for 6.3, for 6.3, for 6.3, draw the equivalent circuit as viewed from the primary side. Okay, the way I see this question, okay, personally, the way I see this question is like the way we dealt with the question using I1, I2. I don't see any division in the primary side, because remember, when you have to speak about the equivalent circuits, it's going to take long. But what I can say, we have exact, and then we have approximate, and then we have the third one whereby the magnetic circuit is removed. So we have one that looks like this, and then here's Z1. Okay, this one is called exact. I think it's exact. I don't remember properly, but we have one that looks like this, and then we have another one that looks like this. Z1 comes before, and then we have this. Z load. So after having this one, we have the last one. Whereby we just have Z1, and then it's in series with our Z load. So it's done. It's like this. Okay. So the reason I'm considering that this last one is the one is because we need to remember that I1 is equals to I prime 2 plus IO. Okay, so the way we dealt with the KT ratio starting from the secondary side, V2, I2, I1, it's like we solve the question in such a way that it doesn't make sense for us to say that we have any magnetic circuit. Okay, because if that's the case, then the only way you can calculate the primary current using the KT ratio. Let me put it this way. The only way you can calculate KT as I2 over I1, it's when you do not have the magnetic branch in your circuit. This is IO. It's when this thing is not there inside your approximate circuit. Why am I saying this? I'm saying this because usually the KT ratio gives us KT is equals to I2 over I prime 2 is the load. I1 becomes I prime 2 is the load. Let me put it this way. I'm gonna explain a lot of things. I'm gonna confuse people here now. Z1 yeah, this is how our circuit looks. Okay, this is supply. This is the approximate Z1. This is Z1. This is Z prime L, and then the current that is flowing here is I1. Okay, so in this case, I1 is equals to I prime 2. This is how it has to be. And the reason I'm saying this is because remember on the other circuits here or here, you had the magnetic circuit. So if you had the magnetic circuit, the current after the magnetic circuit, I1 was going to be here, but here was going to be I prime 2. So when you use KT is equals to I2 over I prime over I1, this I1 is only possible when this magnetic circuit is not there. If the magnetic circuit is there, your I1 becomes I prime 2. So you're going to usually say I2 over I prime 2 because you are having the magnetic circuit. Okay, but because in this case we are told calculate the primary current, and it was possible for us to calculate the primary current using the KT. Primary current is I1. So the only way that it can be possible to calculate the primary current, I1, straight using KT is when this guy is not there. This magnetic circuit is not there. So if this magnetic circuit is not there, meaning I1 is not equals to I prime 2 plus IO is not, meaning now that the magnetic circuit is out, it's not there, IO is no more there. So this makes it what? This makes it I1 is equals to I prime 2, which also makes our KT equation to be I2 over I1, which is what we used in solving this question. That's why I'm saying that this circuit is the one that makes sense for us to go to say that it is the proper circuit for 6.3. Okay, yeah, I'll make a video on approximate circuits to explain more about this. So some of you might be confused about this circuit, how it came about, yeah, but in your book or in the syllabus, there are these 3 kinds of circuits. There's exact, there's approximate, exact, there's, I think that this one is called approximate exact equivalent or something. So this is the one that is possible in this. So this is 6.3. Okay, all right, so yeah, I think we are done. Now we're gonna be solving the last question now. Okay, we're gonna be solving the last question, question 7. This is the question that I couldn't wait to answer. Okay, it's a very interesting question. So let's move on to question 7. Okay, question 7. Copy what is on the screen. Copy. Okay, I'm giving you a chance to copy. All right, I hope you're done. I'm erasing now. I'm erasing. Okay. Question 7. Question 7. Question 7. Question 7. Question 7. Okay. Question 7. Alright, here we go. A 10 kVA 3300 6 volts 50 Hz single phase transformer takes a no load current of 0.8 amps and the power consumed is 660 watt. Calculate the magnetizing and core loss components of the current. Also determine the core loss resistance and the magnetizing reactance. Alright, remember, always write what you're given. S is equals to 10 kVA 33006 volts. Okay. No load current IO is equals to 0.8 amperes. Power consumed is 660. Okay. Remember, they say that the no load current is 0.8 amps and the power consumed, meaning no load, we know it's under a condition that is called open circuit test. It's open circuit, and we know that the power that is consumed on no load when the no load current is flowing is what is the ion. So this is P ion, is the ion loss. So this is P ion 660 watt. Okay, you check out my video on open circuit test, okay, to understand, and short circuit test. Okay, check out my videos to understand on that. So calculate the magnetizing. Okay, calculate IU. Okay, that's magnetizing current. Calculate the core loss component of the current. Calculate IC. Okay, also determine core loss reactance, no resistance. Okay, RC, and the magnetizing reactance XU. So these are the values that they want. Okay, these are the values that they want. They want these values. So one thing we should know about open circuit. One thing we should always know about open circuit is like it's always better when you understand how the circuit becomes an open circuit. Okay. This I explain more when I'm doing short circuit test. Okay. So right now, because of time, I'm gonna write it as it is. Okay. So you have to look at my other videos, watch my other videos to understand how this circuit came about. Okay, this is it's like this. Okay, so this is XU, this is RC, here is IC, here is IU, this is IO, this is I1, and then this is I prime 2, which is equal to 0 amperes. And then the voltage across this is VO. Okay, because this is on no load. This is no load. This is no load. Okay. So, okay, how are we gonna start and solve the question? It's very much interesting. It's very much interesting. So one thing I can tell you about open circuit test and short circuit test is like in the industry, when we test open circuit test, we connect our testing instruments on the low voltage side and then we leave the high voltage side open. That's how we do it in the industry, not theoretically. It's cool when they teach you about that, when you calculate. No, I'm telling you about practical. Okay, you connect your measuring instruments on the low voltage side and then you leave the high voltage side of the transformer open circuit. You connect nothing to it. That's how you properly do open circuit test. Okay, so it's very much important to know which side the test was done before calculating such a in such a question. It's very much important. Don't assume. okay, because this is the theory. That's why it gets tricky. Okay, so what I can say, first of all, before calculating anything, okay, let me just cancel this second because it's very much important. Something is very much important. Always check which side the test was done. So how to check? Okay, I'm gonna calculate I full load 1, which is 10 times 10 power 3 divided by 330, which is equals to let me calculate this. 3,03 amperes, and then I'm gonna have I full load 2, which is equals to 10 times 10 power 3 divided by 6, which is equals to 1666.67. Okay, so now I calculated the I full load on HV, and then I calculated the I full load on LV. Okay, so the electrical rule of machines says that whether I'm doing short circuit test or I'm doing open circuit test in the theory of electrical machines, what I have to do is that I have to check how much is the percentage of the no load current on both sides, and then once I get the percentage of the no load current on both sides, I'm gonna compare the two sides. Okay, and then the side in which the percentage of the no load current is between 2% and 12%. The one that is going to give me any value between these two, it must not be above 12%, it must not be below 2%. The one that lies between 2% and 12%, that side is the side in which the test was done, meaning it's the side in which I'm going to connect my measuring instruments. Okay, 2% to 12%. So let's do that. So I'm going to start and say, okay, high voltage, I'm going to say percentage of no load is equals to IO over I full load 1, which is HV times 100, and then 0.8 over 3,03 times 100. Okay, this becomes it becomes how much? 26,403. Okay, 26,403%. Okay, so I'm gonna continue now and say, okay, for LV side, percent of no load is equals to IO over I full load 2 LV times 100, which is equals to 0,8 divided by 1.1666,67 times 100, which gives me it gives me 0,00 4799%. Okay, so as you can see, the percentage of no load on the HV side and on the LV side, it's above 12%. 26% is above 12%, and 2% is far below 2%. Okay, so this is where it gets interesting, because for me to know which side the test was done, so that I can start my calculations in this question. I need to know which value of no load, the percentage of no load in which side. Is it between 2% and 12%? So in this case, they are both not between 2% and 12%. But what I realize, I know that I cannot operate a transformer with 0% because for the LV side, this is 0%. Meaning like there's no flow of current at all. I can't operate with 0%. I can't operate transformer on no load with 0%. But what I know is that I can operate the transformer at overload. Okay, I can operate the transformer overload. It's not healthy for the transformer. It gives it under pressure. Okay, it destroys the transformer, but it will not destroy the transformer immediately. It's gonna destroy the transformer with time. Okay, but in this case, I will choose 26% because 26% at least I'm operating, even though I'm operating above full load. I'm operating with above the expected percentage. It is above it, but it's operating as compared to the one that is 0%. So 0%, like there's no power, there's nothing, there's no current that is flowing. I can't operate my transformer. But with 26%, I'm operating more than is expected. It's overload, but it's operating. So in such a condition, you choose the one that is higher, which is this side. So if we agree on that one, I can conclude and say, now I know that the test was done on the HV side. Okay, if the test was done on the HV side, this means that the LV side, which is the 6-volt side, was left open. So now I can start my calculations. Now I can start performing my calculations because I know. This is the tricky thing about this thing, and this thing is there in the theory. Okay. Therefore, test was done. Test was done on HV. Okay. Now I know. So what does this mean? Because I was able to do that. Okay. What does it mean? What does it mean? I'm going to show you what it means. Okay. This means that now as I draw my circuit, I know that this is IO, this is I1, RC, XU, and then EO or VO. I know that my VO is 33,000 volts. Now I know. Okay? Because 33,000 volts is on the HV side. It's on the HV side. Okay? So being on the HV side, this guys. So being on the HV side, I can now start and calculate. Okay. I can now start and calculate. So I know that PO, which is ion power, is equals to VO IO cos phi O. So I have my current, I have my power, I have my voltage, I can find my power factor. Okay. Cos of phi O is equals to PO over VOIO, which is equals to the power is 660 over 3300 divided by 0.8. So the power factor is how much? The power factor is how much? I'm calculating here. Okay. This is equals to 0.25 lagging. Okay, I know it's lagging. So the angle will be cos of 0.25, which is 75.522 degrees. So this is the angle phi O. Okay, so I'd like someone to copy that, okay, because this question is long, but it's interesting, so I don't want people to be lost in wondering what am I doing. Just follow me, follow what I'm doing, listen to what I'm saying, you'll understand. Okay, because remember, we're looking for these 4 values. Okay, we're looking for these 4 values, because what I'm trying to do, I think it's better if I explain before time. What I'm trying to do is, because we know that when we're learning about no load, we were given that this is the flux, and then this is IO, and then in phase with V1 here we have IC, and then we know that this is the dot, this is IU, and then this is phi O, 90 degrees. So if we take out that triangle, it's gonna look like this. Triangle is gonna look like this. So this is IO, this is IU, this is phi O, and then this is IC. Okay, so now that we know the angle, okay, I can delete that. Now that we know the angle, okay, inside this triangle that I draw here, the face that I draw here, we know that if we take the cos of this triangle, it's going to be cos phi O is equals to IC over IO, which means that IC is equals to IO cos phi O. Okay, so we can find IC. Okay, we can find IC. IC is equals to IO is 0.8. Cos of phi O is 0.25. Therefore, IC is equals to IC is equals to 0.2 amperes. Okay, this is IC. So we found IC. We found IC. Okay, so we found IC. So this is how you find IC. Okay, so for us to find IU, we are going to have to take the sign of that. So the sign of that is going to be sine phi O is equals to IU over IO, which becomes IU is equals to IO sine phi O. So IU is equals to 0.8 sine of 75. Was it 75? I don't remember. 72. Do that. Yeah, 75.52 the angle. So therefore IU is equals to 0.775 ampere. Okay, so we found IC and we found IU, magnetizing current and the loss component current. These are the two currents that we found. Okay, these are the two currents that we found. So what do we need now? We need RC and we need XU. Okay, RC and XU. So now I'm gonna erase that. I hope you saw how I answered that. You can pause the video if you didn't understand. Okay, so I said that for us to understand this circuit of no load. It's like this. It's like this. Okay, it's like this. XU, this is RC, this is IO, and then this is IC, this is IU. So this is VO, VO, VO. So for you to find RC, RC is equals to VO over IC. So we found our IC. We found IC. We already found IC. IC is equals to 0.2 amps. IU is equals to 0.775 amps. Okay. So now our VO is 3300 divided by 0.2. Therefore, RC is equals to 16.5 kV. This is 16.5. Sorry, kilo ohm, not kV. This is RC. Therefore, RC is equals to 16.5. 16.5. This is our RC. RC, which is called the Colos resistance. Okay, so this is our RC. So the thing that we need lastly is the magnetizing reactance. Okay, so I hope I'm making sense here. I hope I'm making sense. It's very much important for you to understand. Okay, I wish I started this question early though. So for XU, as you can see that VO is across this. So it's the V, is the R, is the I. Okay, just like I found RC, I'm going to say XU is equals to VO over IU, which is equals to 3300 over 0.775. Therefore, XU is equals to 4.25. Okay, that's 4.25 kilo ohm. Okay, so yeah, we answered the questions, question 1 to 7. Okay, that's how you deal with the question. Always, for the last time I repeat, in question number 7, whenever you meet such a question, always start. In fact, for you to solve short circuit test and open circuit test, unless you are told in which side the test was done, you must always perform the calculations that I performed, that I showed you. You must check if the percentage of the secondary and the primary side are between 2% and 12%, for you to be sure that in which side are you gonna perform your calculations. It's very much important, because without doing that, you will never answer the question. That's how you answer the question. Okay, so I'm gonna solve more questions like this in other videos. So I thank you for your time. I thank you for cooperating with me. Thank you so much. I wish you understand. I wish you understood everything that I did and all the techniques. So thank you so much. Take care. Expect more solving of questions from me that are related to this. Thank you so much. Take care. Cool. Sharp.